We start with basics. There are forces, tension, compression, bending, and shear. First one is a fairly easy concept, and that is of tension, one thing pulling on another. When you pull on something like steel, which is probably the best structural material that we have that resists tension, failure normally would be slow, and you would be able to see necking down of the tension before you fail. The rescue site, the things that we will see is like is shown in the slide, a piece of concrete hanging from the structure, and an engineer that's knowledgeable would quickly know what the capacity of the reinforcing bars are that are hanging the piece, and could make some kind of a judgment about whether it's a good situation or a bad situation. The next kind of force is compression, and compression is a little trickier than tension in that two kinds of things will happen with compression. If a structure is very fat, as is shown on the left, the structure will crush very, very slowly when it's extremely loaded, which is the best of that kind of a situation, so that when you see a failure, it'll fail slowly. If it's a very thin structure, on the other hand, it will buckle, and when something buckles, we would call that a catastrophic collapse. And a catastrophic collapse happens all at once. The structure buckles, and the upper part of the structure ends up on the ground, and it's a very sudden collapse, is the kind of thing that we would not like to see in a collapse. And we use that knowledge when we build our shoring, in that we make the shoring, for the most part, fat and short and with lots of bracing to keep the vertical posts from buckling, and so that we can see crushing in the sole and in the wedges. What happens in that case is that wedges will actually cup up a little bit, and you can observe if the shoring that's been installed is inadequate, and then the rescue forces can build better shoring or more shoring. Third concept is that of bending. Anyone that stands on any floor, like the floor I'm standing on, the members underneath them are bending, and what happens in bending is that the bottom of the beams or slabs will extend and get in tension, and the top will shorten and be in compression. And that's important to us when we look at concrete structures, because in concrete structures there's reinforcing steel placed where the tension will occur, because concrete is very weak in tension, and we add the structural steel or the rebar to it, which takes that tension. And when a structure has been loaded extremely, what we'll see is a pattern of cracking that you see in the slide, vertical cracking towards the center of a span, and diagonal cracking towards the end. And the cracking in itself is an indication that the structure has been loaded extremely. And what we do then is we observe that or monitor those cracks, and if those cracks don't change, we can make a judgment that the structure is still fairly viable. And the ways that we monitor the cracks can be as simple as painting them with red paint, and then if one can see white lines through the red paint, eventually one knows that the cracks have opened a little bit. So that's what that information is helpful to us in making judgments during an incident. The last concept is shear, and shear is something that happens to planes or walls, and when the walls are loaded laterally along the edges, the structure or the piece of the wall tries to change from a parallelogram from a rectangle to a parallelogram, and this concept will cause the center of the plane to lengthen, which will cause diagonal cracks in concrete structures. And when one is loaded in one direction, going to the left, let's say, you get a crack in one direction. When you turn it around and go to the right, you get a crack in the other direction. And then earthquake damaged structures, what we see is X cracking, and that's what that X cracking comes from. The whole concept of the parallelogramming we call racking of a structure. And we will see in subsequent slides many structures that are racked, and that's a cause for concern, of course, and then some judgments are made about that. The next topic that we want to talk about is how materials behave, and there's sort of two extremes in behavior that we will find at a disaster site or in any building. One is brittle behavior, which is illustrated by this little piece of wood, or can be illustrated by a piece of wood where When you break it, it is catastrophically broken. Once that happens, the structure is destroyed, and that is contrasted to ductile behavior, which is where parts of a structure will bend and not break and give you a warning when the structure changes shape, illustrated by a wire where if you push on it a little bit, it will rebound, but if you push on it with great force, you will actually cause the wire to bend, and it has the almost magical property. You have to keep pushing on it to keep it bending, and you can reverse that force in the wire, and it'll bend back and forth, and that's how earthquake-resistant structures are designed, with lots of steel in them that will do this through the cycles of an earthquake. And the materials that we normally build with are wood, steel, reinforced concrete, and masonry. And of those materials, we could start with wood and say, well, wood does break as illustrated, but when you put a wood structure together with lots of sheathing and plywood and so forth, you can find that it is actually makes a fairly ductile structure. Or if you think of cribbing is crushed, it crushes and deflects and is quite ductile. Steel, as illustrated, is the king of all structural materials. That it's very, very ductile, can be put together. If it's put together properly with adequate connections, it performs very, very well in most any extreme condition. Reinforced concrete comes in sort of two varieties. One would be cast in place, or CIP concrete, or could be precast concrete, PC concrete, where the cast in place, one has a much better chance at having a fairly ductile structure where the joints being properly done make a structure pretty much a continuous unit. Where precast concrete itself, the precast elements built in a factory can be very, very strong, but the joints in them will determine how ductile the building is. If the joints are done very, very well with good steel embedment and so forth, that can make a fairly ductile building. But if they're not, as is the case in a lot of the U.S. Away from earthquake zones, those structures may be quite brittle. The reinforcing, that is the steel that is reinforcing concrete, taking those tension forces we talked about earlier, may be the reinforced steel or deformed bars, which are called rebar, as you probably know, or it could be cable that is pre-stressed, a very high-strength cable that's pre-stressed within the concrete. The cable may be, in precast concrete, may be stressed ahead of time, and then the concrete is cast around it, which still makes a fairly good structure bonded together. But there is a class of structure called post-tension concrete structures where the cable is laid in a sheath in the forms before the concrete is poured. The concrete is poured around that. Cable is then stretched and anchored at the ends of the slabs. And that kind of a structure, normally those are parking structures or first-story structures in apartment houses, can be problematical because if that slab is damaged at one end, the cable then is loosened and the entire structure is in question. So that's not one of the favorites of rescue engineers, kind of structure for rescue engineers. Reinforced masonry, properly reinforced masonry may behave relatively ductilely, where unreinforced masonry is probably our most brittle material, and many, many buildings throughout the U.S., especially the central U.S., in the central earthquake zone around St. Louis and so forth, hundreds of thousands probably of unreinforced masonry structures exist.
I'm Pete Keating. I'm a structure specialist with Texas Task Force 1, also a professor of structural engineering at Texas A&M University. Now, buildings, they all have to resist loads. There are two general types of loads that need to be resisted. There are vertical loads or gravity loads. It comes about from the self-weight of the structure and the members, and also from its occupancy, or what we call live load. Structures also have to resist lateral loads, and we'll talk about those shortly. But the vertical load have to be resisted and basically collected, carried out through the members, and the load safely brought down to the foundation. The elements in the building that collect this load, the vertical load, are roof systems and floor systems. They'll transfer the load out to beams that support the floors and roofs. These beams then subsequently are carried out to the columns, and then the columns take the load down to the ground. And again, we have to, as structural engineers, safely get the load at its point of application down through the system to the ground. And you can think of this as a plumbing system or analogy where the tub or basin collects the load, the piping system brings it down through the system into the ground. For vertical loads, we have two basic systems. One is the framed, the other one is the unframed system. The framed system you can think of as a set of beams and columns, also as like a skeleton. The unframed system is actually made up of a series of what we call bearing walls that, again, take the load out of the roof or the floor system down to the ground directly. Typically, when we talk about structural collapse, what we find is because of the longer spans or greater distances between columns that can be gained in a frame system, that when we do have a collapse, the collapse zone is larger, whereas in the unframed system, that the spans generally are shorter, hence the collapse zone will be smaller. As in all cases, and we'll see this throughout the presentation, that where we have the most problems is in the connections. The other type of load that must be resisted by a building is the lateral load. Again, examples would be from the types of forces that get generated during an earthquake, or certainly wind loading. Basically, the lateral load tries to push the structure over. Now, the buildings, as far as lateral loads go, can be broken up into three different systems, and they differ on how each resists the lateral load. One is a box building, the other two are moment frames and diagonally brace frames, and we will look at each of those. The box building basically is a building that is carrying the vertical load or the gravity load by bearing walls. In order to prevent the structure from being racking, what we need to do is put in walls that can resist the racking. Typically, we call those shear walls. As an example, you can use the analogy of a shoebox. If you subject a shoebox to a lateral load, what happens is that the load pushes in the wall facing the load, but ultimately gets transferred out to the side walls, and then those are the shear walls, and then the load then goes out to the foundation. And what you need to realize that a very important element of a box structure, and actually all structures, is the floor or the roof, and we call that a diaphragm because that helps transfer the lateral load into the lateral load resisting system, be it a shear wall or we'll see the columns in a frame system, say. The second type of building system for lateral loads is the moment frame. There, what we are doing is, again, it is the frame system, but in order to resist the lateral loads, what we are doing is we're providing a rigid attachment between the beams and the columns. What this does is actually develop a resistance that allows us to transfer the lateral load down to the foundation. The third and last type of building system is the brace frame. Again, it's a frame system, the beams and columns, but now what we are doing is using diagonal bracing to carry the lateral load down to the foundation. What we may do is use a single diagonal brace, or more typically, particularly in lighter type structures, we use a pair of diagonals. In the figure shown, we are using a single diagonal to resist the lateral load. Under its action, the diagonal goes into tension. Typically, it is easier to resist a tension force than it is a compressive force because of the problems of buckling in the compression member. Sometimes what we do is we use a pair of diagonal bracing such that regardless of which way the lateral force acts, one of those diagonal members will go into tension. If we only use a single member, then that member has to be able to resist both tension and compression. Another concept that we need to look at is one called redundancy. Basically, redundancy is having one or more load paths in a structure. We sometimes refer to this as the belt and suspender system, such that if we have failure in a member, that there is an alternate load path for the force to travel down to the foundation. Otherwise, collapse may ensue. Again, normally we have redundancy in many of our structures, but as we get into larger structures with greater spans, there's a tendency to have less and less redundancy. Again, the redundancy are collapse preventers. In fact, in use our operations, when we go back in and place shoring into a damaged structure, basically what we are doing is adding or improving the redundancy of the building. Sometimes we have unintended redundancy. An example of this would be a partial collapse of a floor system, as you see in the lower portion of the slide. What happens there is the floor will then form what we call catenary, which is basically like the cable of a suspension bridge. Now the floor, instead of carrying bending, actually goes into tension and will carry load and may be prevented from further collapse. The problem with this unintended redundancy is that we need to look at what effect it is having on the rest of the structure. A suspension bridge only works because we anchor those cables somewhere to the ground. And in the same way, if a catenary unintentionally forms in a structure, we may be adding a significant tensile force to that structure, and we need to look at those areas for the integrity.